In our last video, we're going to go through and ask ourselves, why do things float? The concept of floating is known as buoyancy. For an object to float, the net forces on that object must be zero. So in order to go through and examine which of these blocks, A, B, or C, would be floating, or whether they would rise or sink, we need to learn a little bit more about the buoyant force. Archimedes' principle tells us that the magnitude of the buoyant force equals the weight of the fluid that's displaced by the object. So that means the m in your mg is going to be equal to the density of the fluid times the volume of your object, because your object is displacing that volume of fluid. So you calculate your volume based on the volume of the object, but the density used isn't the density of the object, the density is that of the fluid. And that'll give you the amount of the buoyant force. So if you want to go through and figure out if an object sinks, floats, or otherwise, the only difference here is the difference in densities. So an object is going to sink if it weighs more than the fluid that it displaces. So basically, if the average density of your object is greater than the density of your fluid. Now the opposite is going to be true if an object floats. If an object floats, that means that its density, that means that it weighs less than the fluid that it's displacing, meaning that its average density is less than that density of the fluid. And we're using ρ_f for density of the fluid. So if an object is going to be neutral, just sit in the middle of a fluid and not rise or not sink, that means it has neutral buoyancy. That object is going to be motionless if its weight exactly counters the weight of the fluid that's being displaced. Or in other words, that the average densities of both the object and the fluid are the same. So scuba divers, for example, when they're underwater at a specific depth, can go through and change the amount of air in their vests to change their average density. And they want to try and get that density equal to that of the water so that they float motionless inside the water. Let's take a look at an example of this. In our example, we want to determine the density of an unknown liquid. We notice that the block floats in this liquid with 4.6 centimeters of the side of the block submerged. When the block is placed in water, it also floats, but this time with 5.8 centimeters submerged. What is the density of the unknown liquid? So first, we need to figure out the volume that is submerged when the block is in the unknown liquid and when it's in the water. So the volume of the block when it's in the unknown liquid is going to be equal to the area of the top of the block times the height of the block that happens to be submerged. So that's our 4.6 centimeters. When the block is in the water, we calculate our volume the same. We just have a different height this time. Area is the same, but the volume of the block is now going to be based on a height of 5.8 centimeters submerged in the water. Now again, if we want to know what's going to go on with this, whether it's floating or sinking, in both these cases it's floating. It's floating because the amount that's submerged exactly equals the amount that's being displaced by the water. So our density of the unknown liquid times the volume of the block inside the unknown liquid, which is the same thing as the volume that's displaced, is going to be equal to mg. The density of water times the volume of water that's displaced is also equal to mg, because the block is the same. It hasn't changed. It's still the same block that it was before. So that means that the density of the unknown liquid times the volume displaced in the unknown liquid is equal to the density of water times the volume of water that's displaced. I divide both sides by the volume of the unknown liquid and plug in for the fact that volume is the area times the height that's displaced, I can go through, plug in my numbers. I'll see that the area cancels. And I can find that the density of our unknown liquid is equal to 1,260 kilogram meters per meter cubed. So if we go back to our table and we take a look at what this value is, it's closest to glycerin. So that's most likely what this particular unknown liquid happens to be. Now lastly, I want to talk about boats. We're talking about things that float. Boats are going to be the most likely thing to come to mind. We're going to examine an idealized boat. Physicists like to examine things as nice and easy as possible. So this boat is basically a rectangular prism. So it's got sides of height h and an area of A. We'll imagine it's some sort of rectangle. And there's no curves here. It's nice, solid right angles everywhere. So that makes it easy to go through and calculate the volume. So if we want to know how or whether or not the boat will float, we have to go through and look at the geometry of the boat to see if it allows the boat to displace enough water to equal the weight of the boat itself. Again, if we want things to float, then the average density of the object needs to be less than that of the fluid. So let's start with examining the volume of the boat. That's going to be the area times the height of the walls, which means that the average density of this boat, which happens to have a mass m naught, is going to be that mass m naught divided by the volume of the boat, which we can rewrite as m naught over A times h. This boat will float if that average density is less than the liquid that it's in. So we'll assume water, seawater, whatever it is that you want, but less than the fluid that it happens to be. This explains why oil and water separates, why you see one on top of the other, and I'll leave it to you to go through and take a look at the table to determine which one should be floating on top of the other.